Let's say we have a function f of x and we know that we can differentiate it, and we are hoping that there is some way to make it look like a straight line, say. We want it to be very similar to a straight line, or even maybe a quadratic, or maybe even a cubic, or a quartic, or like a quintic, or like, oh, I forgot my cubed, or something as big as possible, basically, like this. Now, the only thing that I need to know is what is A0, A1, A2, A3, A4. So, what we do is, we say, well, if this is always going to be true, or certainly near 0, say, doing Maclaurin first, near 0, then f of 0 would need to be A0 plus A1, well, 0 plus, so all these are just going to go, aren't they? So they're all going to go. So f of 0 must be what A0 is. Y at the point 0. Okay, let's take our original thing and differentiate it. F primed of x equals, so that gives us A1 plus 2A2x plus 3A3x cubed plus 4A4x. No, can't differentiate, that's squared and that's cubed plus da da da. Now if we put 0 in again, f primed of 0, then everything cancels apart from that A1. So now I know that f primed of 0 is A1. Now let's differentiate again. The second derivative is given by 2a2 plus 3 times 2a3x plus 4 times 3 a4x squared plus blah blah blah. So the second derivative at the point 0, put 0 in everywhere, gives me 2a2, which means that the second derivative at the point 0 divided by 2 is equal to a2. Let's differentiate it again. The third derivative is going to be given by 3 times 2a3 plus 4 times 3 times 2 a4x plus blah blah blah. So the third derivative at the point 0 will just be 3 times 2 a3. So that gives us that the third derivative at the point 0 divided by 3 factorial, 3 times 2 times 1, is a3, and you can see where this is going. So the next time I differentiate, I'll get 4 times 3 times 2 a4, and then everything else will have zeros in. So when I put 0 into the fourth derivative, I'll just get 4 factorial, 4 times 3 times 2 times 1, times a4 is the fourth derivative at the point 0, and that gives me the general formula, which is that the an, the nth coefficient, the coefficient of x to the n in the expansion, will be 1 over n factorial multiplied by the nth derivative of the original function evaluated at the point 0. So that gives us the full Taylor expansion with all of the coefficients of the x's given by this formula. So what happens if we're focused at the point A rather than the point 0? Well, let's have a look. If we're focused at the point A, then we're trying to find a polynomial in extending powers of x minus a, and we want that to roughly equal f of x near the point A. So we can do exactly the same thing but introduce a's. F of a is going to make all of these cancel apart from the first one, giving us f of a is a0 is f of a. If we differentiate everything, f primed of x is equal to a1 x minus a plus 2a2 x minus a. Oops, that shouldn't be there. a1 plus 2a2 x minus a plus 3a3 x minus a squared plus 4a4 x minus a to the 3, etc. Now if we put in the point A, then this is going to go, everything's going to go apart from that first one, so that gives us that a1 is f primed at a. Now let's differentiate again. So we get 2a2 plus 3 times 2a3 x minus a plus 4 times 3a4 x minus a squared plus etc. And if we put in the point A to both sides, we'll get 2a2 plus, and then this is going to go, everything else will go. That gives us that a2 is equal to 1 over 2, the second derivative at the point A. And one more time, if we differentiate again, we get 3 times 2 a3 plus 4 times 3 times 2 a4 x minus a plus blah blah blah. When we put the a into our third derivative, we get 3 times 2a3. Everything else is going to be gone. That gives us a3 is 1 over 3 factorial, the third derivative at the point A, And you can see that in general, if we keep repeating this, we're just going to get that an is always equal to 1 over n factorial times the nth derivative at the point A.